Well, hello everyone. Welcome to my garage. Today we're talking about class layout. It sounds like one of those things that you have to know, but really don't want to. It's kind of like tax law or something like that. Something that's useful, but is probably not that interesting. And when I started writing this talk, I thought it was going to be short. I thought, maybe 3 or 4 slides would do it. And as a result, I have more than 100 slides here for you, not all of which we'll get to. So I'm not going to waste any time, head right into it. Why do we care about class layout? Well, there are a lot of reasons. One is efficiency. One is we may write our algorithms, our implementations of algorithms with a certain format in mind. And if you're not aware of class layout issues, you can actually write code that will work almost all the time and then will fail in spectacular ways at odd times in the future. Another reason you might care about class layout is if you're writing code for hardware, you're using memory mapped devices. And of course, the layout of those classes has to correspond to the actual hardware it's being mapped to. So it turns out to be quite an important area. And of course, C++, in its wisdom, can take a simple area like that and make it somewhat complex. So let's look at a very, very simple class. Here's your human resources department. They have a scary looking function called terminator. It takes pointers to different types of employees. And the implementation contains this enum, a static data member, and then some non-static data. So how is this actually laid out? What occupies space in the class? Well, it's pretty much the same thing as this C implementation. In C, actually, the enum is at the same scope as the struct. It's pulled out of the struct. But the static data member has static lifetime and external linkage, so it's pretty much the same implementation as a global variable, although it is in the scope of the class. So the only members that cause the layout of the class to be affected are these non-static data members. And of course, storage for non-virtual member functions does not affect class layout either. And the reason for that, of course, is they're implemented typically as in the same way that a regular member function would be. But let's talk a little bit about them. I mentioned that I've been writing some embedded C++ code to bare metal, hardware that has no operating system, whatever. C++ is terrific for writing to bare metal. But the only negative is that a lot of people who work in that area don't trust C++. They're afraid it's going to bulk up their programs. It's going to be hard to write efficient code. As it turns out, C++ is much easier to use to write very, very efficient code for embedded systems. But it is indeed more complex than C or perhaps some other language you might be using. And so when you see simple code like this, I'm calling a function called terminator that simply fires 3 people in different ways. I know, I should find a better example. People worry, well, what's the overhead for doing this? And why shouldn't I just write a regular old non-member function like this and pass a pointer to the HR object to these various functions I'm invoking here? Well, you could, but then you're losing out on encapsulation and all those other nice language features. And in point of fact, if I compile these 2 different functions, this being the member function and this being a non-member function, they generate precisely the same code, exactly the same code up to the names of the functions. This function, of course, is in the scope of the HR class. This one is not. And so this is well, I don't know about you, but I'm tired of seeing x86 code all the time. So I'm using ARM assembly here. I find it much easier to read and deal with. But the point is we get the same behavior. There's no penalty whatsoever. Okay, so getting back to class layout, what about the layout of these non-static data members? And so here I've unnecessarily had some public followed by private, followed by public, followed by private members. So how could these be laid out? Well, in traditional C++, basically we were told, and it was the case, that the only guarantee we had is that non-static data members in the same section, this public section, would be laid out in increasing addresses. So we know that B would follow A. We know that D would follow C, but any other ordering was quite legal. So you could, even though most compilers didn't do any reordering whatsoever, a traditional C++ compiler could produce these two orderings, which, as it turns out, are no longer legal in modern C++. In modern C++, we have a different guarantee. It sounds similar, but it's quite significantly different, that members with the same access have to be laid out in the same relative order. So in this case, there's no reordering. This is correct. A, B, and C were declared lexically in that order, and their layout has to be in the same order. But they could be reordered like this, maybe have all the public data members first, followed by the private, or maybe have some sort of random ordering like this, or have all the private members first, followed by the public members. I did see somebody hack a compiler once to do this, and it was legal. And it was done to do object level protection instead of type level protection. So there is some variability in the possible layouts of your class. Well, what about base classes? Well, that's unspecified. The order in which the base class subobjects are laid out is completely unspecified. It's typical that they're simply laid out in the order they appear on the base class list. But in this case, we do see different compilers behaving in different ways when they're trying to optimize storage use. Sometimes the compiler will permute the order of the base classes in storage in order to shrink the size of the object. Okay, hope everybody's still with me. So empty base class members. Well, we often have stateless objects. You might have a closure of a lambda expression that has no data, doesn't do any captures, it has no state. Types or objects can be stateless as well. For example, this empty class is a stateless class, and this empty E is a stateless object. Nevertheless, every object has to have some size. The likely size of these two queries is probably 1. It might be 4. It might be some minimal size if there's an alignment requirement on this architecture. But again, even if I have 3 empty objects, each of them will occupy at least 1 byte. And so the size of this class is probably 3 bytes. That's dispiriting. But in C++20, we're all looking forward to C++20. We have an attribute called no unique address that allows a compiler to have these 3 data members share storage space. So the size of this class object is now likely to be 1 if the compiler does collapse these 3 members into a single address location. Okay, so that's a nice thing to look forward to. And this is actually great if you've ever, in your spare time, looked at implementations of STL containers. A lot of times a container is parameterized by things like, in this case, here we have a hash map of some sort. And again, I stole this from the working draft for C++20. Sorry, I borrowed it. I leveraged it. I don't know what the correct term is. We often have parameterizations of these classes by stateless, typically lambda functions or function objects, like this hash function, a predicate for comparing things in the hash map, and an allocator. These are often stateless. And in the past, if you looked at a really high quality STL implementation, you'd see some incredible template metaprogramming going on, asking if this is stateless, instead of having a data member, I'm going to have a base class of that type in order to potentially get the empty base class optimization. So you'd see all this very, very fine-grained, complex code in place to shrink the size of these various typically stateless function objects. Well, now we can simply say what we mean. We can say this thing isn't required to have a unique address. So that if this is an empty type, it may share space with these other empty types as well. That's nice. Have you noticed that C++ is getting easier and easier to program in over time? We used to have to be actually really intelligent to write good C++ code, and now you can kind of just, I'm just kidding, guys. Now it's a lot easier to take care of things like that. But going back to the empty base class optimization, again, a lot of times base classes are stateless. They're just a bunch of type defs, static members, member functions, whatever, that don't actually occupy any space inside the class. And so the point of this optimization is to allow the compiler to do precisely what the no unique address attribute does. It says this base class can share space with other base classes. So different compilers have different levels of success with this. Just a minor point. I mean, if you go back and look at this, let's go back a few slides. I got lost. Here we are. What's so important about saving 3 bytes? Well, it might be 8 bytes. It might be, I don't know, some fair number of bytes. The point is that most of these containers use what's known as a handle body idiom or a pimple idiom or a bridge pattern to implement themselves. We have a small handle that points off to some potentially large implementation. I don't know. Maybe this is a map. So this is a balanced binary tree. The thing is that in modern C++, we're often using the return value optimization to return containers. If we can't do a return value optimization, the backup strategy is to try to do a move. Well, if I want to move this enormous data structure, if I want to return it from a function, and I can't use the return value optimization for one reason or another, if this is a really small handle, if I can shrink it down to like maybe 16 bytes or so, I can just return this in a pair of registers and overwrite this other handle and do a move operation. So shrinking these handle classes is of paramount importance if you're trying to have very, very efficient copying and returning of these containers. Oops. Okay, so this does turn out to be important, and we would go to great lengths to try to use this empty base class optimization. So without the optimization, we may see something like this. Many compilers, compilers are increasingly doing better at this, but historically, a lot of compilers would only optimize the first base class if it was empty. So by having a non-empty base class subobject first, followed by an empty one, would give us no improvement. This subobject would still occupy space. So we would sometimes do things like permute the base classes. So the empty one was first, so it could share space with this non-empty. And just looking at various compilers in preparing this talk, I noticed that there is still a large variety of levels of ability to apply this optimization. It varies quite widely among compilers. Compilers are allowed to compress out a sequence of empty optimizations. Some compilers will even do a very aggressive optimization. In one case, one compiler actually moved the storage for empty up to the front so it could share space with non-empty one. So it actually permuted the order in which the storage occurred so I could do the empty base class optimization. Some compilers would not optimize away a sequence of empty base classes. Others would optimize an arbitrary sequence of base classes. Again, so this is a very difficult to predict optimization. And it's very difficult to predict in some portable way a complex C++ class layout. So if you're concerned about layout, it really would be nice to have some sort of guarantees from the standard. And we will be looking at that. But before we go on there, let's look at an important distinction between lexical and physical ordering. A lot of the language is defined in terms of lexical ordering of class components. A member initialization list initializes in the order of declaration. No matter what order the actual storage is reorganized by the compiler, it uses the lexical ordering of those members to initialize in that order. Base class subobjects are initialized in the same way in the order they appear on the base class list. And another example, if you have a defaulted Spaceship operator, it compares members in their declared order. And that's important because this is supposed to be some sort of lexicographic ordering based on the values of the members. So again, lexical ordering is guaranteed by the standard, but physical ordering is not. So here, excuse me. Here is a simple class, Flatland. Z is of no importance in Flatland, apparently. And I've decided to default the implementation of the Spaceship operator. So what do I get for free? Well, I'll compare the x's first, then the y, then the z, even if z is pushed up to a 0 offset. It'll still be compared less, so I'll still get a correct lexicographic ordering. Here's where problems come. Maybe you're trying to heavily optimize this and you feel that doing a mem comparison instead of a member by member comparison will give you better behavior. Well, this should ruin the rest of your day looking at this, wondering if this is appearing in your code somewhere. Not that you would write something like this, but someone else. What could possibly go wrong? Well, again, this is supposed to be a lexical comparison. If I move z, if the compiler chooses to move z up here, then I will now have a broken comparison because it's going to compare z first, then x, then y, and give an incorrect comparison. So this is a really scary sort of thing to see in your code base because it may have been working for years and years and years, and then maybe you get a better optimizing compiler, and all of a sudden it fails. That's too bad. So as usual, the solution here is to act like an actual person and put all of your data members in the private section of your class, keep Scott Myers happy, keep everybody else happy, and then this might work, but it's not guaranteed to work. I'm still doing this memcmp, this bit-by-bit comparison. I know that x, y, and z occur in that order, but this could still fail. That's scary. Why could it fail? Well, we'll come back to that in a minute. But let's take a quick segue and look at a piece of hardware. This is a UART, Universal Asynchronous Receiver Transmitter. This is an actual piece of hardware from a very old board that's very instructive because it's such a complex set of memory map devices. So this is a device from that particular board. And we might try to do something like this. We'll define special register to be a volatile 32-bit integer. And then we hope that this layout is going to match that of the actual hardware. And in fact, it does. Unless you have a very unusual platform, this should match pretty exactly. But you don't want to take chances. So what we'd like to do is have some actual guarantee. And we want to make sure that each of these members has the proper offset, the correct sizes, and so on. And so since C++11, we do have such a guarantee, and that's a guarantee of a standard layout type. A standard layout type is basically a simple type or a standard layout class. And a standard layout class has no virtual functions, no virtual base classes. It can use multiple inheritance, can have 0 or more base classes of standard layout class types, no 2 base classes of the same type. That allows that optimization of collapsing base classes. And the important thing is that all members have the same access control and all members are declared in the same class or the same base class. Now, with this restriction, we can say that UART is now a standard layout class. And this is going to make reasoning about the layout much more tractable. We've simplified things to the extent where we can now actually reason about this layout in a platform-independent way. Just an aside, there's an older type trait called POD for plain old data. Plain old data is very, very restrictive, and it really is not a very useful concept, at least for most problem areas. You don't really want to know if something is plain old data. We want to know if its layout is predictable. We want to know if it's a standard layout class. So in fact, the isPod type trait is being deprecated in C++20. And you're encouraged not to use this concept, but instead use something more precise, like a standard layout concept or something else like that. And this is, again, what most hardware programs have been doing all along. And this just makes it a legitimate, guaranteed behavior. Here's the problem. If I go back quite a while, I say that this is still not perfectly safe, even though I know the order of X, Y, and Z are the same. The lexical and the actual physical ordering is the same. This could still fail, this bitwise comparison. And the reason for that has to do with padding bytes or slack bytes. So the only guarantee we have about standard layout classes is that the first data member is at offset 0. And that the data, and we know that the data members will occur in increasing address locations, or non-decreasing address locations at least. And this also means that you can legitimately reinterpret cast the address of a standard layout class to a pointer to its first non-static data member. And that's about the only time reinterpret cast is guaranteed to give a certain result. So basically, we do know that the first register in our UART will be at offset 0. But we can't really be sure about any other data member. And so even a standard layout class data member can have slack bytes or padding bytes, depending on the architecture on which you compile it, and depending on things like Pragmas. So again, Pragmas are non-portable. I'm not a big fan of using Pragmas. I want my code to work the same way on all platforms if possible. But I can say I want to pack and set the alignment to be 4-byte aligned, or I might want to pack things maximally by doing something like this. I've never actually used these in production code because they scare me. The trouble is that they don't work uniformly. So usually the best thing to do is to make your best effort and then confirm that it was correct. Static assert is your best friend whenever you want to have some certainty in your program, especially about lower level things like class layouts. So here we're doing a static assert saying, I expect that the offset of the ucon member in the UART structure or class is 4. In other words, it's this occupies 4 bytes and there is no slack bytes between the ulcon and the ucon. Static assertions are wonderful. I might be exaggerating, but I may have as many static assertions as regular executable code whenever I'm writing to a piece of hardware. Offsetoff is an old-fashioned macro. It works for standard layout types. It may work for other types, but it doesn't have to. So if it doesn't work for other types of classes, that has to be documented. So conditionally supported means that offsetoff may work for other classes, and given implementation should document what it does support. In my experience, it works for almost everything. A few outlier cases where it may not work. So again, this again is a compile time check. And if you're like me, you're a nervous person, and I check everything because it's not only that I don't trust myself and I don't trust hardware, I don't trust people who maintain my code. And actually this kind of normative distrust of yourself, your maintainers, of everybody leads to a very nice stable situation. The more questions you ask, the more you make sure that you are correct, the more stable things are. So this kind of normative distrust of everything does lead to a nice, stable environment. That's actually a result from sociology, which I wish we had time to discuss. So here I'm checking the size of the special register, the alignment of the special register. I want to make sure it's unsigned. And I want to make sure that this is a standard layout class. So there is a type trait that will tell me whether UART is standard layout. So if somebody does something like make one of these functions virtual, UART will no longer be standard layout, and I will find out at compile time. Here is an even scarier memory map device. Here's a timer. And it's scarier because here I have a character mode register. And yet the data register has to be at offset 4. And if it isn't, and this timer is in somebody's pacemaker, people will die. Here's a count. It has to be at offset 8. If it isn't, your intelligent toaster won't work and people will have burning toast or whatever. So this will actually affect real world things. So we do want to make sure that this data is indeed at offset 4. So of course, use a static assertion. Well, what if it's not at offset 4, but we want to force it to be? Well, we can use an align as attribute. And here we want to align this data to be 4-byte aligned. And that should be all we have to do. But I always check anyway, just in case. And we'll see why. Now, I don't speak Russian, but this is trust but verify, a very popular phrase in the mid to late 1980s. And it's a good piece of advice. Trust, but I also want to verify it. There's no cost for verification. Well, suppose you're a really nervous person and went ahead and aligned everything to 4 bytes. Okay, that's not going to hurt. It's probably overkill, but I still want to check. Because here's what can happen if you don't check. I shouldn't say this, but have you ever noticed how your code starts to break in mid-May? Bugs start appearing. Why is that? Summer interns arrive, and they'll do something like this. They'll do a Pragma pack. I want single byte alignment if possible. Well, I've observed that different compilers behave in different ways. Here I've aligned everything to 4 bytes. Compiler A does indeed do that alignment in spite of this Pragma. Compiler B listened to the Pragma over the align as and gave me the following incorrect offsets. So it really makes sense to use these static assertions no matter what. Even if you feel they're overkill in this case, things can change in the future and you want to catch these things. Otherwise, toast will burn. So again, I strongly, strongly recommend using static assertions whenever you want to confirm something that can be stated at compile time. So here is not quite a flatland class, but a narrowland class. So we have X, Y, and Z are the usual coordinate labels. And I have a comparison operator that compares 2 narrowland objects. And I've decided to optimize this again. So here I'm going low level. I'm doing a memcmp to compare these 2 objects of type narrowland. And so it's just going to treat this as, oh, let's say this is 24 bytes. It'll just look at these 24 bytes as bits and confirm that the bits are the same in both cases. Well, that makes me a little nervous, but this makes me even more nervous. Because this is narrowland. I don't need a long for the X coordinate. So I turn it into a character. I use an unsigned character instead. And now, however, this has not changed the size of narrowland. So this comparison operator is still comparing all of this data, including this padding data. this can give us some really, really unusual results. Things can act normal for quite a while. So here I have a global variable. I know, but it's just example code. Here's a global variable. And then I enter the function g. G as a local variable, and I'm comparing the local variable and the global variable. And we expect these to compare equal. They have the same values for the same members. And in fact, they do. So if I execute main and I call g, these will compare equal. Great. And then some tiny change happens. I decide to call f first. Now they don't compare equal anymore. What happened? Well, initially, global was initialized to all zeros. At the start of the process, memory is 0, so it has an all zeros initialization. And then this is copied into it. But also, the runtime stack was initialized to all zeros. So when I entered G for the first time, this memory just happened to be zeroed. And so these 3 slack bytes here compared to these 3 slack bytes here as equal. They were both 0. Then I decided to call some other function f first. F wrote something to the stack frame, then returned. G reused that stack frame, and now these 3 bytes were no longer necessarily zeros, and these no longer compare equal. Again, this is the kind of thing you want to avoid. So my usual recommendation would be, just don't do this until you're sure that it's a really important optimization for you. It's just too sketchy, too touchy, too easy to get wrong. But suppose it really is important. Well, I mean, obviously, the best fix is just to be a normal person and do the comparison that you intend. But if this is important, the nice thing is we now have type traits that can let us ask questions at compile time. So here we can rewrite this operator to ask the question. If narrowland has a unique object representation, in other words, there are no slack bytes sitting around, then we can do our fancy memcmp implementation. Otherwise, if it doesn't have a unique object representation, then we'll do a normal member-by-member comparison and get the correct result. Notice that I've used a const expert if here. This probably wasn't necessary. This is a compile time constant. It's either true or false. Every compiler on the planet will properly optimize and do the code elimination for one or the other of these 2 alternatives. But the const expert if is, it guarantees that the code will be eliminated. So you won't have unusable, unreachable code sitting around in your process. Okay, so this asks the question at compile time and then makes the correct compile time choice and retains either the memcmp or the normal implementation. We didn't have time to talk about this, but if you look at the type traits in C++20, there are all kinds of terrific new type traits that let you ask things like, are these 2 classes layout compatible, and so on and so forth. Lots of nice information that can make an optimization like this actually safe to do. Okay. I recognize we're covering a lot of material pretty fast. Let's talk a little bit about single inheritance. A lot of people have seen diagrams like this. It's still useful to review it. Here's a base class of some sort, has 3 virtual functions, and has other stuff. We're just going to think about the virtual functions. And this base class is not an abstract base, so we're actually pointing to a B object here. Now, ordinarily, if this were a polymorphic base class, I'd like it to be abstract. But in this case, for purposes of demonstration, it's not abstract. So I have a B object, I'm pointing to it. This code generates something like this. The BP points to a B object. A B object is almost certain to have a V pointer, a virtual function table pointer, that points off to a virtual function table that contains an entry for each of these virtual functions. It also has some other stuff here, which turns out to be quite important. So what is this other stuff? Well, virtual tables over the years have become kind of a dumping ground for anything related to the type of a class. So in addition to pointers to virtual functions, there might be an offset to the start of the complete object. What does that mean? Well, this is a base class. It may not be a B object, but maybe a base class sub-object of some other object. So we might have instead a pointer to the start of the complete object, which is otherwise unknown. A pointer to the type info, that's important for doing dynamic casts. And offsets to virtual base class sub-objects, which we'll talk about shortly. Very interesting stuff, actually. I think Arthur O'Dwyer gave a really nice talk in CppCon 2017, where he talked about how do you write dynamic cast from scratch. And to do that talk, he talks a lot about what this other stuff in the virtual function table is. So it's a good thing to watch. Another side point is that if this were a proper polymorphic base class, it would have a public virtual destructor. I've decided to ignore those because they do make things a little more complex. In particular, a lot of implementations will have two entries in the virtual table for a single destructor. One is a deleting destructor that frees the memory, and one is simply a destroying destructor. So that's not really important to the subject at hand. Okay, what about the calling sequence? Well, the calling sequence is pretty simple. We grab the v pointer, we indirect to it, we access the function of interest at its proper index, and then pass BP as the this pointer, something like this. It's very, very efficient compared to many other languages, a lot more ornate, but code like this can be rendered pretty quickly. Here's a simple ARM assembler, and again, this is a RISC machine, no complex instruction sets, and yet we have a very, very reasonable sized implementation here. Very fast, comparatively fast. If you're not into reading assembly language, well, everybody is now. Everybody knows about Compiler Explorer, and so it's a good idea when you're wondering how efficient something is, just to say thank you to Matt Godbolt and go to Compiler Explorer and see what kind of code you're getting. Okay, overriding. Well, the derive class, derived from this public base class, is going to choose some overrides. Here we're going to override F1 and F3 and add a new virtual function F4. The effect of this is now that the base class subobject of the complete object still is a v pointer, but now it's pointing to a different v table. And this v table is a little bit larger than the base class one because I've added a new virtual function. And overriding is simply replacing the address of this function with a derived class version if overriding has taken place. So F1 and F3 have overridden. F2 was not overridden, and so this still refers to the base class version of this function. But notice that the actual sequence, now I have a base class pointer pointing to derived class object. The sequence is still the same. I still branch indirect through the v table, go to the corresponding offset, and whether this is a base class object or a derived class object will get the correct behavior because the constructor for D has set the v pointer to the v table for D, not the one for B. So most people have seen code like this. If you've been programming in Python or something, you may not be aware of this, but very, very simple mechanism, very fast and type safe. I do want to point out that the standard does not require that virtual functions be implemented anything like this, but I've never seen a compiler that didn't implement virtual functions like this. Earlier compilers, Cfront in particular, would put the v pointer not at offset 0, but at the end of the base class. And so you'd have a structure that looks something like this. And this difference led to some very dangerous code there was a lot of code that assumed that the v pointer was at offset 0 and would actually do a reinterpret cast equivalent. This was done some time ago to grab this v pointer and do something with it. But unfortunately, that code would not work very well in a situation like this. It would grab this v pointer, which of course is not there, and do something really unfortunate. So remember, there is no guarantee that the class will be laid out any particular way in this case, or that there will even be a v pointer. But I think it's pretty universal now that the v pointer is generally at offset 0 by default, because you get better behavior that way and so on. And then we have multiple inheritance. Very exciting. So here we have an observed shape that is a shape and a subject, so it's being observed. In that case, we have a layout something like this. So an observed shape object has a shape subobject, perhaps followed by a subject subobject, then some derived class members. This is a likely layout, not a guaranteed layout, but a likely one. But notice, if I have an observed shape, and then I do a safe and predefined conversion to the base class subobjects, well, both of these base classes, if they're non-empty classes, can't have the same address. And so it'll wind up with something like this. This observed shape pointer points to the complete object. The shape pointer points to the first subobject, and the subject pointer points to the subject subobject. But notice the pointers point to different locations. So basically, in C++, an object can have more than one valid address. This observed shape object has at least 2 valid addresses. It could have more, but it's likely to be something like this. The nice thing about this, though, is that the compiler does know what this delta is. It knows how to take this base class pointer and get to the complete object, knows how to take the complete object pointer and get to the base class subobject, because this is information that's known at compile time to the compiler. So what does this mean for pointer comparison? Well, in C++, when you compare 2 pointers, we are not asking the question, do these pointers point to the same location? The question we're asking is, do these pointers point to the same object? That's quite a different question when you have multiple inheritance, and even when you have single inheritance. So in this case, when we're comparing the observed shape to the shape, there's not much to do here because they actually do have the same address. But if I'm comparing an observed shape to a subject, I have to do some arithmetic. The compiler has to add that delta to the derived class to get the address of the base class, conditionally add, of course, because if this is a null pointer, I want to see if the subject is also null. Otherwise, I'll add the delta and do the comparison. So this turns out to be a pretty efficient operation. So again, the compiler knows, okay, subject is a non-first base class of this observed shape. Therefore, I'll look up the delta in the symbol table, I'll do this addition, and then do the comparison. And in the simple risk machine, it's really, really fast. Most of the deltas are fairly small, and so they can often be immediate data. And this simple 3 instruction sequence does that addition and comparison and so on. Of course, if no adjustment has to be made, it's even faster, but it's not that much slower. And this is, of course, also the way static casts will work as well. If I were to cast, say, a subject to an observed shape, well, I do the same delta arithmetic. Of course, I do want to be clear about this. If I cast a subject to an observed shape, I'll subtract this delta. I had better be sure that this subject is indeed a base class subobject of an observed shape. If it's a standalone subject, well, I'm going to have a bad address here. So as always, static cast is just dangerous enough to be fun when you use it in hierarchies. So let's get a little more detailed here. And a little bit faster. So here are a couple of base classes. I'm not going to stress this too much. So they each have a v pointer in them. What does a derived class that derives from these two base classes look like? Well, it has two base class subobjects and therefore has two v pointers. That's a little scary. So now we have more than one v pointer. And here's the problem with overriding. If the derived class object is overriding a non-first base class virtual function, well, it's something like this. So say I overrode D overrode F2. Well, it's going to override B1's F2 and B2's F2. The trouble is, this is a pointer to a B2 subobject, but this function is expecting a pointer to a D object. So I have to do that delta arithmetic on this pointer to get past a correct this pointer to this overriding derived class function. So here is the first implementation, and this was done intentionally for portability sake. The first implementation of multiple inheritance would actually have a delta in the virtual table. And this delta was almost always 0, but it would occasionally have to do some delta adjustment. And so we'd have a non-zero delta in the virtual table. And this is a little unfortunate because we always had to do that arithmetic, whether we had a non-zero delta or not. And again, this was done intentionally. Bjarne was aware of other implementations, but for practical reasons, he elected to do this in order to make sure that C++ could compile everywhere, be translated into C without forcing an assembly language approach. Later, when that became less important, we had a somewhat better approach called a Thunk implementation. The term Thunk actually comes from Algol 60. It's a way to do pass by name, but it's, I said it was misnamed. I guess it's an extension of the concept of a Thunk, but it's just a little snippet of code that does that delta adjustment and then passes it on to the eventual receiver. So in this case, instead of storing the delta in the virtual function table, I, instead of putting df2 here, I put the address of the Thunk. And what does the Thunk do? It forwards the call after doing that delta arithmetic. And this is a fairly, very successful, actually, way of implementing multiple inheritance because this delta adjustment is a relatively rare thing, relatively rare. So you don't want to penalize all virtual functions for that. And this works very well. We even see this manifest in other areas, which I'd love to discuss, but we don't have time to. If you have a pointer to a member function, there are two major ways of implementing that. One of them actually uses a Thunk to distinguish between a virtual member function and a non-virtual member function. So without penalizing the typical case where you're taking the address of a non-virtual. So again, very successful technique. And some compilers, I believe the Solaris compiler did this, would just have the Thunk adjacent to the body of the overriding function. So we simply branch a few bytes before the address of the function, execute the delta adjustment, and then execute the function. So again, these are various ways of dealing with that. What about single inheritance? Well, you can actually get multiple addresses under single inheritance if you're not careful. If I have a base class with no virtual functions, and I have a derived class that has a virtual function, that's not unheard of, but it's a little unusual. You might have a layout like this. The D object contains a V pointer, a B subobject, and then the rest of the D members, but the B subobject is not at offset 0, it comes after the V pointer. It's allocated in this location. You can also get this if you have no virtual functions. If I have a virtual base class, the same thing can happen. The virtual mechanism is not guaranteed to, but may be implemented with a virtual function table. So even if you have no virtual functions, if you have a virtual base class, you may find yourself with a virtual pointer, and you can have the same situation here. So just be aware. Just a warning. This is a bug. If you have a code base that has code that's 20 years old in it, this bug is in your code somewhere if you haven't found it yet. This is a very, very common bug. We've seen that under multiple inheritance, certainly, but even under single inheritance, sometimes we have to do delta arithmetic to do the correct address transformations. And this delta arithmetic depends on the compiler knowing the exact types of the pointers that are being converted or casted. One thing to emphasize is that C++ is a strongly typed language. And whenever you do something that reduces that strongly typed nature, particularly by casting, you're inviting disaster. So you want to be very careful. So here we have an observed blob of some sort. And we can convert it to a pointer to a subject. That's a safe conversion. Converting this address to this address is fine. This is not a good idea. Here I'm converting a subject pointer to a void star. This is a very dangerous conversion and one you wouldn't do lightly, or unless you were, trying to ruin your organization or something. The trouble is that now these different addresses compare equal. These different addresses don't compare equal because this is a void star pointer. The compiler doesn't know what it's pointing to. It can't perform this delta arithmetic. Well, what's the problem? The problem is that people would have interfaces like this. They type def something to be a void star, something you probably shouldn't do. And then they have a nice looking interface, a set widget and a get widget. But this widget is really just a void star. So people would set a widget with a derived class. Now, if they get widget and cast that void star back to exactly the same type, this is guaranteed to work. It's guaranteed by the standard. But what people did was this. They assumed that base classes and derived classes had the same address. A base class subobject was at offset 0 of a derived class. That was never guaranteed. It was just often the case. So now when we set the widget, this is a void star, we cast it back to the base class. Well, under multiple inheritance, this is not going to work. It's going to cast that void star to not a shape. It's going to cast it to a subject, but leave the compiler thinking that that pointer is a pointer to a shape, and you're going to have some undefined behavior. And if you're lucky, you'll die horribly immediately. If you're unlucky, it's, well, not pretty. Okay, and what happened to people's code is code like that worked very well for a long, long time. And then somebody made a remote change. When the code was recompiled, even though it wasn't modified, now it's going to break. Somebody decided to use multiple inheritance, and that broke the entire framework. So again, you want to be a bit careful. I'm not going to emphasize this. This can happen under single inheritance as well. Again, we always obey the standard, even if it seems like we don't have to. Their history, at least the history of the past, ignored the standard and then got later problems. A common example I see is it's okay to delete a null pointer, that's fine, but you can't delete it twice without resetting the value to some valid pointer value. If I delete the same pointer twice, if it's not null, you'll get probably a segfault. If it is null, it typically just happens to work, but it's not guaranteed to work. And there was actually one compiler in the 1980s where it wouldn't work, because when you deleted a pointer, a new value was overwritten in the deleted pointer. So again, do follow the standard. One last topic in record speed. I want you to know that I was warned that this talk was too long, and I ignored the warning, as always. So what happens if we have two sub-objects of the same type? Well, two base classes of the same type in the class lattice, we're going to have two sub-objects of that same type. This might be correct, but it probably is not. Just think if it's a reference count, nothing good is going to come of this duplicated reference count for a single object. So the best thing to do in a case like this is typically just to redesign, get rid of that reference count, and just do external reference counting, use a shared pointer or something like that. But if for some reason you can't, then we can use virtual base classes. Now, virtual base classes, in my opinion, is always your last choice. But again, sometimes it's the right choice. It's just not the right choice very often, because they do make a lot of things very complex. And we'll see a couple of them right now. So once I declare a virtual base class, now I have a single A subobject. Where is the storage? Inside of a B, inside of a C? Answer is typically pasted to the end of the complete object. So a D object looks something like this, is B and C subobjects, and it has a single A subobject at the end of the storage. A B object looks different. Its A subobject is also at the end of the complete object, but obviously at a different offset from the beginning. Well, this is a bit scary. So here is a non-virtual base class, very simple. Again, it's not guaranteed to be here, it could be here, but the compiler knows where it is. If I have a pointer to a DB object, the compiler knows where to find this base class subobject. And if I want to access the members, the compiler knows, okay, I have a DB pointer, I know where that subobject is, so I can access it directly and efficiently. That's good. Once I add a virtual base class, now things get complex. Now, assuming the compiler does this, the shared subobject is pasted to the end of the complete object, and now we have a V pointer to information that tells us where to find the subject. So a DB object looks something like this. I have my DB derived class members, then my base class subobject here. Well, what if this DB object appears inside of another class? In that case, we'll have something like this. The subject is still at the end of the complete object, but it's no longer adjacent to the DB. Now it's at the end of this other object. So the information that's stored here differs from the information here. Here's information that says you can find the subject subobject so many bytes from this location. This says same thing, except it's a different value. Obviously, it's going to be increased by however big this other part of this containing object is. Early implementation, again, worked fairly well. It actually stored pointers to the subobject. It turned out this was problematic for a number of reasons. For one thing, we couldn't bitwise copy an object of this type because that would result in bad addresses here. So the typical implementation is as you see here. We have a virtual pointer, even if we don't have virtual functions. So again, here's a picture of the situation. I have a pointer to a DB. The compiler doesn't know statically where the subobject is, so it has to go over here, grab the delta, and do some delta arithmetic. And things have gotten considerably worse. This simple access is now, it looks pretty expensive, or relatively expensive. Formerly, it was quite simple, but now I have a lot of work to get that delta and apply it correctly. So again, I don't want to badmouth virtual inheritance. It does indeed solve problems, and it has been used very, very effectively by a lot of people, but it's not your first choice. If you do use virtual inheritance, I recommend use it with interface classes. Since an interface class doesn't have any data except for a virtual function pointer, very little can go wrong here. You won't be accessing any data in subject for the simple fact that subject does not have accessible data. Okay, that's the end. I was very optimistic, but that's not going to happen. So thank you for your patience. And any questions, I'd be happy to take them, or you should know where to find me, I hope. just write to me at stevedewhurst.com. You'll find my email address there.